So, hi Devu. Since no one else is in the session yet, let's wait for like 10 minutes before we get started. So that I'm just waiting for a few people to join the session. Hi all, hi to everyone who's watching on YouTube. So since no one has joined the session in person yet, like since it's the last problem solving session, let's just wait for like 5 more minutes. If someone shows up, if no one shows up, then anyways I'll start with discussing the problems. But yeah, for now we'll get started in like 5 minutes. So hi Saravya, we'll just get started in 5 minutes. Just waiting for like maybe a couple more people to join the session. Anyways, if no one else shows up, we'll get started in like 5 minutes. Okay, so since no one has joined the session in person yet, I guess we can get started nonetheless. So there's an issue with my camera, so I won't be able to open my camera. So hello to everyone who's watching on YouTube. So just to reintroduce myself, I'm Lakshya Sargi, the problem-solving TA for the NPTEL Social Network Analysis course, and this is going to be our last problem-solving session for this semester, as it's like 12th session. And we'll be discussing again the topics, a brief overview of topics discussed in this topics discussed in this week's lecture, and some questions based upon them. Although this week most of the lectures were based on like conclusions we can derive uh, from the topics which we have studied throughout the course. So yeah, so we'll be discussing that. And just as a reminder to everyone, so even though this is our last problem solving session, but still tomorrow, like Tuesday, 6 to 8 p.m., we'll be having a summary session, a 2 hour summary session, where I'll summarize, where I'll essentially summarize uh, everything which has been discussed in the course so far. So obviously it won't be a very concrete summary, but I'll try to rope in as many topics as I can, which have been discussed throughout the 12 weeks of the semester. So yeah, so we'll be having a session tomorrow from 6 to 8 p.m. For this summary session, and hopefully I'll see some of you guys in person. So yeah. So other than that, I don't think there are any other announcements to make. So now I guess we can get started with the session then. So yeah, I'll just share my screen and we can start with discussing the topics and yeah, some problems related to that. So I'll just share my screen. Mhm. Yeah. So so this was week 12, and in this week, essentially, like I already said, that uh, we mostly discussed like case studies and conclusions we can derive from the topics which we have discussed throughout the course in the first 11 weeks. So yeah, so uh, so whatever we have learned till now is a lot of theory, right? It's a lot of theory regarding uh, social network. It's a lot of theory regarding like social networks analysis. Like, you suppose you're given some network, and now how can you essentially analyze that network based on some metrics and so on. Uh, but note that in real world, the thing is you're not essentially like, first of all, in real world problems, you're not essentially given directly like, okay, this is the graph, and you have to find like clustering coefficient in the graph, or maybe some other thing in the graph, or like finding communities in the graph. What you are given is a very high level problem statement that maybe some people, and those people like something, but they don't like something else, and now we want to find some like-minded people and so on. So this modeling of the problem as graphs has also be done, it needs to also be done by us. It's not that someone has already given us a graph and we just need to find out like stuff related to that, mathematical stuff related to that. First, it is very important to model the problem as like relevant social network also. So, so whenever we are trying to use the topics which we have covered throughout this course, or which we have learned throughout this course, our first step will be essentially like modeling the given problem using some kind of a network. So essentially, we'll try to represent the given problem as some kind of a network and then find the relevant characteristics of the network. So first of all, how do we model the problems into networks? Because statements can be so the main so essentially note that this is also not an easy task. First of all, like modeling some given problem using networks, some problems cannot be even modeled as networks because sometimes the problem statements can be very imprecise and can be quite complex. And then suppose even if you succeed, so there are levels to difficulties in using social network analysis on real world problems. And although these are difficulties, but yeah, these require ingenuity, but nonetheless, they are very helpful. Then suppose you have even modeled the network, then the question arises, can we employ different network algorithms on the model network? Suppose our objective is to find, let's say, like-minded people in a group of people. Suppose we have modeled this problem as some kind of a network where people are given by node. Then maybe we want to find out, we want to cluster these nodes into communities because each community represents like-minded people or something else. So can we use the network algorithms which we have learned so far on the model networks? And then here the complexity arises: when do we choose which algorithm, and how do we even use that algorithm? So yeah, and yeah. So and also we'll also have we'll also discuss some case studies where these networks which we have discussed are actually used for some real world use case, like studying malicious activities in online social networks. And like these kinds of techniques which you have already learned were also used for identifying identifying the spread of the COVID-19 pandemic. And these are also used in recommendation systems, which is a very huge research area on its own, because recommendation systems is something which companies like Amazon, Netflix, and all of these just throw loads of money into recommendation systems so that user recommendations improve over time. Yeah. So whenever we are trying to model a problem using networks, uh, usually it's good to divide a use case into two parts. First of all, the background and the modeling, and then the methods which we'll use and the consequent discussion. So let's come to the first kind of use case which we'll be discussing. Suppose one wants to identify malicious activities on online social networks. So the online social network, suppose we are on the internet, and note that like on internet there are all kinds of entities which which are present in the internet. So some entities can be malicious, also some users can be malicious and can try to uh, do harm to the social network, or yeah. So there are, so we note that we are not studying these malicious users in terms of viruses or everything, but we are studying these users in the context of social networks. Like how can these users affect this social network? We are not discussing about the virus and all. So what can happen? So there are different kinds of online misinformation available, which is which can lead to very bad consequences. Like spreading of misinformation can lead to bad consequences, as you may be aware of, like various instances from the news and everything. So there are different kinds of militia activities. So for maybe like one kind of activities. So let's say these are like on the scale of like green is the lightest, like this is the least harmful and or like least intentional, and this on this red scale, as you go along, you are like going into more intentional malicious activities. So one kind of activity is satire, where there is no intention to cause harm but has the potential to fool someone. Then there can be activity like false connection, where headlines don't support the actual content. Like this is usually what you also call clickbaiting. Like headlines of the article are different from the content of the article. And then there is misleading content, where misleading use of information to frame an issue or individual. Where suppose someone tries to uh, state the facts in such a manner, like hiding the complete truth, but stating like facts in such a manner that someone can be framed from that. Then there's false context, where genuine content is shared with false contextual information. And then there's imposter content, where genuine sources are impersonated. Then manipulated content, where genuine information is manipulated to deceive. And then, like, I think most intentional is this fabricated content, where 100% fake content is designed uh, to deceive someone or harm someone. So, yeah. So, these are different kinds of malicious activities on online social networks. And mm, uh, usually it's good to identify these kinds of activities so that yeah, because as I said, the spread of misinformation can cause a lot of issues. So if one identifies these kinds of activities as soon as possible, then one can stop spread of this misinformation. So yeah. So there can be the malicious activities on online social networks can be like false or harmful. So false activities are generally spreading misinformation, where false connection and where it has like false connections and misleading content. Then in harmful activities, there can be malinformation where someone leaks something or harasses someone or like posts a hate speech. And their intersection is the most harmful, which is disinformation, where one can spread false context, manipulated content, fabricated content, and so on. So it is harmful and also it's not true. So yeah. Uh, so maybe like as we already said that first step in whenever we are solving these kinds of problems is modeling the problems into networks. So let's just see some popular models for some like famous social networks. So for example, let's take the network of Facebook. So suppose one has to model the network of Facebook, so there can be like uh, different kinds of models. It's really up to you what you decide to put as nodes and what you decide to put as edges. So this kind of model is not unique. Oh, so hi Karpagam, I just noticed that you joined. So we are just so right now we are just discussing that the introduction to this week's topic where we discuss like how do we model a problem using networks. And yeah, one announcement which I already made Karpagam just to reiterate for you. So this is our I think so this is our last problem solving session because this is week 12. But note that there will be one session tomorrow, Tuesday 6 to 8 p.m., which will be a summary session. So there I'll be discussing a summary of the content discussed over 12 weeks. So same timing like tomorrow, Tuesday 6 to 8 p.m. So I'll also post its recording on YouTube. So if you're not able to make it to the session, I'll anyways post it. But just wanted to inform you so that if you want to join, so you can join tomorrow. Obviously, I'll discuss very high level summary because uh, you can't really cover like 12 weeks of contents in 2 hours. So yeah. Okay, cool. So I was just describing so suppose one has to model some network, so there can be different kinds of models which one can use. But like we are just giving an example which these kinds of models are generally used. So suppose you are modeling the social network of Facebook. Although one can create different kinds of models where one can say, okay, like uh, I'll have users as nodes and maybe edges will represent their posts or something else and so on. But this is one of the more wider used models where you have nodes for three kinds of entities for users, the posts, and the groups. And then there are different kinds of network links between like these nodes. Uh, there are friendship nodes which are between user. There are reactions on posts which are like user and posts which are between one when one node is a user and when one node is a post. Then there can be an edge based on reaction. And then there are links like creation of posts where one user creates the post. Then there are nodes for messages, then nodes for like group memberships, which will be between users and groups. So something like that. So this is one popular model usually used for Facebook. I note that for different kinds of online social networks, these models can be different because Facebook has these things like users, their posts and groups and something, but maybe a network like Instagram or Reddit has like some other entities. So for example, suppose you want to model as graphs the network of Twitter or X, which you call it these days. So the types of nodes can be users, the unregistered persons, the posts and groups, and then there can be different network link types like between user there can be a following like if one user follows another user, that can be a link. Reactions on posts, creation of posts, messages, group memberships. These are kinds of similar to Facebook network. But yeah, like this following is maybe not present in Facebook. There you have a node or like link for instead for like friendship and not follows. Okay. So then like maybe let's just take another network for example. So LinkedIn. So in LinkedIn again you can have so LinkedIn is like as you can see it is like more complex than Twitter. So there you can have nodes for like users, unregistered people, posts, groups. the skills and jobs of the people. And there can be networking types like connections, group memberships, posting, reactions on posts, messages, endorsement, invitations, and recommending jobs. So yeah. So suppose you have to maybe like suppose you have to create your own, you have to code your own LinkedIn or at least a backend for the LinkedIn. Then maybe you can use these kinds of entities, and this can lead to a good type of abstraction. But yeah, nonetheless, uh, maybe now we can move to like maybe so yeah, so maybe another kind of a network which suppose one has to okay, so now right now we have discussed like some networks and like how can we possibly model those networks. So let's just see maybe so this was also discussed in the lecture. Suppose you have YouTube as your online social network and you want to model this YouTube as maybe some kind of a graph or a network so that you can perform whatever we have learned throughout the course. So you can perform some algorithms or something on the resulting graph. So what kind of nodes can you take and what kind of links can you take? So one example can, so again, as I said, like there's no such unique network, but one example which can be done, at least in the context of YouTube is, so you can have nodes for video. So this was just in the lectures also. So you can have maybe nodes for videos as well as different users on the channel. And maybe like, uh, if two you so a user video link will be maybe so a user and a video node will be linked if suppose that this user has watched this video, and similarly if this user has also this video watched this video, then maybe this video has two outgoing links for the two users which who have watched this. So you one kind of a network can be this kind of a network where you just want to store maybe what user has watched which kind of video. That kind of information can be stored in this kind of a network. Then you will have maybe an alternate network, suppose on your based on your use case. Suppose you just want to represent maybe interests of users or something. Then maybe you can have a network where just the nodes are users, and each link represents each link has a weight associated to it, and the weight is essentially the number of common videos which both the users have watched. Suppose these two users have watched five videos, like these users have five watched videos in common, then or maybe like 50 videos, then like this link will have a weight of 50, and similarly you can assign weights to other links also. So yeah, this is these are like this is how maybe you can model. This can be a very bare bones, a bare minimum model for a YouTube network. But again, like you can make some more complex networks based on our use cases. So suppose because on YouTube videos also one can comment, one can like, or yeah, one can subscribe on channels. So you can have notes for channels. Suppose if you want to make it more complex, and then yeah, then you have playlists and so on. So yeah, one can get as complex as possible. But if one just needs to get started, then this is a very good bare bones model. So okay then maybe we can discuss. So suppose if we have like realized like how can we model some kinds of networks, then comes maybe one of the main tasks at hand, like uh, related to misinformation or malicious activities on online social networks. So one of the most common malicious activities is, so you might be familiar with it, is sock puppeting in OSN. OSN is nothing but online social networks. So so one can have like sock puppeting in online social networks. And what are sock puppets? So sock puppets are essentially uh, user accounts controlled by a puppet master. So suppose sock puppets on a very high level are like maybe so suppose one person owns or has bought like suppose thousands of accounts. So essentially that person has access to thousands of accounts, and using some maybe script or some bot or something, that person can post using these thousand accounts simultaneously or something. So essentially these thousand accounts uh, working on the uh, like are working on the backend call of only one user. So essentially these thousand accounts are sock puppets of that one user. So that's how this term came about, sock puppeting in online social network. So this puppet master, the original user, owns at least another account in the network, and then the objective is to engage in malicious behavior in the network. Suppose if you have like multiple accounts on the same network, and you can like access all of them, so then you can influence the network in like very strange ways. Like suppose there is a very informative, so like maybe let's not discuss this, but on a very high level idea, suppose there is some kind of a news article or something posted on Twitter. So suppose someone posts some kind of a news on Twitter, and then what you want to do is you don't want people to know about that news, or you want people to think that the news is false. So what can you do? Although if the news is in reality true, but what you can actually do is maybe like as soon as you see the post, you can have your account and your thousand other owned accounts comment simultaneously on the Twitter post that, oh, actually this news is false. And maybe when someone like later on when someone accesses this post and sees these multiple comments saying that this post is false, one might actually be convinced that yeah, maybe the tweet is actually not true. Although if just one account posted that this news is false, then still a new user will take it at a new reader will take it with a grain of salt. But if thousands of people are simultaneously saying that this news is false, then you will probably believe that the news is false indeed. So this kind of a thing is very like very commonly used to influence these social networks. Yeah. So, like I said, the sock puppet accounts collectively manipulate discussions or behave as trolls to spread hateful contents. So, yeah, and yeah, on a broader definition, if you want to define it in one line, original online social network user account controlled by a puppet master who owns at least another user account. This can be a broader definition for sock puppeting. So, yeah. So then it becomes like really necessary, really important because these sock puppets can hold a lot of power or a lot of leverage in the social network, and these can have like very malicious consequences or very bad consequences. So that's why it's very important to identify and stop these sock puppets in these online social networks. So mm, yeah, so the task at hand is maybe identifying sock puppets in these networks. So note that although single user is maybe like tied to multiple accounts, but it's really different to know the identity of the owner of the account. Like you cannot know, it's really difficult to know whether all of these accounts have the same owner because and so these sock puppets cannot be explicitly recognized because of amount of anonymity allowed in registering users. So normally, whenever you register on a social network, you're not allowed for like all kinds of details. Maybe like in Gmail or something, you need to enter your like phone number or something. But it's not always the case that you need like some information which ties the account to you uniquely. Like so like it's usually not the case that your identity can be determined using your account, and this is usually allowed for because people want anonymity in the network. So then one cannot explicitly identify which of the accounts are sock puppet accounts. So one needs some alternative strategies, and maybe that's where what we learned so far in the course comes into the picture. So yeah. So maybe like Wikipedia considers the following as features of a typical sock puppet. So some common features of that sock puppets are accounts that make similar edits, accounts that post at similar durations because all the bots suppose are working at the same time, and accounts that post from the same IP address. Of course, like if someone has multiples of accounts, and so the person will operate from single place, so the IP address for all these accounts will more or less be the same. Although these kinds of things can be like maybe surpassed or something because like one can use VPNs and so on to overcome these kinds of issues. The puppet master can overcome these kinds of issues, but yeah, on a very high level, these kinds of things are usually features of a typical sock puppet account, right? So then it's like But so like how do we actually identify these sock puppet accounts in the online social network where this network maybe has millions of nodes? So one needs some kind of algorithm on it. So Kumar et al. In 2017 gave some very nice ideas on maybe how one can identify these kinds of sock puppets. So maybe let's not look at a diagram, but rather a text. So suppose, so if these are the kinds of things which we consider as a typical software account, so one thing what one can do is we can select users based on IP addresses, remove the top 5% of the most used IP addresses, remove the top 5% that make account of the accounts that make use of too many different IP addresses. And then one can select users based on temporal proximity, like accounts that post in the same discussion within like some T minutes, where T can be set to like 15, 20, whatever your choice. And then one can select users based on number of discussions commented upon. So yeah, so the users which comment on like multiple discussions are usually people who are like owners of stock profit accounts, because on a very high level, like these stock profit accounts are made to engage more in this social activity to harm people. So yeah, so normally like if you are a genuine user, you won't be commenting on too many posts in a day, right? Uh, you will be maybe commenting on like one or two posts whatever you have read. But if someone's intention is just to spread as much malicious content as possible, then one will uh, post to a lot of discussions or contribute to a lot of discussions. So usually sock puppet accounts have a lot of like, so the sock puppet users participate in a lot of discussions. So these kinds of criteria can be used to maybe identify which of these are sock puppet accounts. But this is a very vague high level idea. Like it's not the in-depth algorithm of Kumar at all. For that you can read their research paper and everything. But yeah, on a high level, these guys Kumar et al. Actually observe some other things about these social networks. And like so in the network analysis of sock puppets, like maybe a reply network of an online discussion is a network where each node represents a user, and edge from node A to B indicates that A reply to B's post at least once. So suppose first we define this reply network, and then there were some observations uh, like which these Kumar and guys show in the network analysis of the sock puppet accounts. So the observations they show is that sock puppets tend to interact with other sock puppets a lot because they want to boost each other's discussion quantity. And then they are more central in the network than ordinary users. And these sock puppets tend to have higher page rank than ordinary nodes. And why is this true? Because these sock puppets are interacting a lot with each other. And if they are interacting a lot with each other, everyone is boosting each other's importance and uh, in general like each other's page rank a lot. So yeah, so this is the high level idea. And then like Kumar et al. Also observe that if one looks at ego networks of sock puppets, I hope everyone remembers what are ego networks. So ego networks are basically for any node, its ego network is essentially that node along with all its neighbors, and yeah, the induced subgraph on these set of nodes. So Kumar et al. Compared the ego network of sock puppets and ordinary user nodes, and what they observed was like so from ego networks also they were able to derive some insights on like how one can flag maybe some accounts as sock puppets and things like that. So they observed that there is no difference in terms of number of nodes and density of the networks. However, the sock puppets exhibit a higher average clustering coefficient, and they initiate more conversations in general, and they are very active when they are engaged in discussion. So these kinds of things uh, are usually used to identify these sock puppet accounts. So essentially, like I hope you guys understand that these sock puppet accounts, what I'm talking about, are what one also calls these kinds of bots, like some kind of bot accounts. So, so essentially, the what we want to do is like identifying these kinds of bot accounts, and these are the kinds of things which these are the kinds of observations which we can see like how these bot accounts are functioning. And so, like if we take all of these observations into account, whatever we identified, maybe we can assign some kind of probability that okay, maybe this account is a bot with very high probability, or this account is suspicious, or this account is not suspicious, and so on. Okay. Okay, so this is a very high level idea. And now maybe like one other way which can be done is uh, okay. So from this network analysis and ego network sock puppets, after this, yeah. So this was the idea of Kumar et al. To how to on how to observe sock puppet account. So you can go into this in detail in maybe if you read the paper, you can go into the detail of this. But another way how one can handle these things of like identifying sock puppets is sock puppet prediction, where one tries to predict which of the accounts are sock puppet accounts and so on. And usually these involve some kinds of machine learning models and so on. So one can have ground truth data collection strategies and behavior analysis fed to a supervised machine learning model. So this is completely different from like Kumar et al.'s discussion. And features other than network features will be fed into the model, like linguistic traits, profile behavior, community participation traits, etc. And then one can have maybe some kind of link analysis on these kinds of things. So if when one wants to like perform some kind of link analysis on these sock puppets, suppose first we define the terminology what is a serial puppet master. Serial puppet master is somebody who is actively and repeatedly involved in social network as a puppet master. So yeah. So several brands, political organizations, or social media celebrities hire these puppet masters to defend their reputation or promote their products. Like, I think that everyone knows these kinds of things. Like, anyone who wants to get famous on social networks hires these kinds of puppet masters. And yeah, so sock puppets in a group often have similar attitudes to most topics. And this is how maybe you can predict like which are sock puppets and which are not sock puppet. So Bu et al. Actually proposed this creation of a network based on this similarity of views. So so before this, these Kumar et al. Guys, like they tried to do this network analysis on ego networks and like these kinds on the social networks, like by some different criteria, like identifying which of the accounts are stock puppet accounts and so on. However, Bhu et al. Gave an alternative approach to it, like one can actually leverage machine learning to see how the to identify these stock puppet accounts. So what they propose is okay, like even though these stock puppet accounts can be like uh, different accounts and they can have like some different behavior or something, but on a very high level, like the purpose of a sock puppet account is essentially to maybe boost the views of another account, right? If you have multiple accounts, you want to essentially maybe boost some certain views. So you say, okay, thousands of accounts at the same time should spread this same view or the same opinion. So that's why the sock puppet accounts will tend to have similar attitudes to most topics or similar opinion on most topics. So who at all leveraged this and created a network based on the similarity of views. So the accounts which share a lot of similarity, like on different kinds of topics, will probably be sock puppet accounts, or they will at least be flagged as sock puppet accounts. So the challenge here is like how to define what do we mean by similar attitudes. So as I already said, maybe the attitude here can be in connotation to whether they share the same opinion or they differ from the opinion or something. So if how does one model the attitude consistency, at least in the Wu et al.'s paper? So uh, what they essentially say, okay, like maybe let's not get into the math. I don't think a lot of math is anyways discussed here, but so they use machine learning models and on a very high level, a token is the smallest possible unit of a. So they take every sentence and divide it into tokens. Like this is done in any NLP model. Like and a token is the smallest possible unit of a sentence. And the connotation that a given token carries can determine whether a token is positive, negative, or neutral in nature. So, for example, like if one says amazing, it's a positive token, awful is a negative token, and city is a neutral token, and they can be assigned like various weights. And now, like one can assign like maybe orientation of a user towards a given topic by determining the comment which the user has made towards that topic and seeing whether that comment supports or opposes the topic. And then you can have these orientations which can be like defined using these scores. And uh, the more the users with the same kind of scores on different topics across various topics, more is the reason to believe that these users may be like connected to the same puppet master. So yeah, and so like just in coordination of that, so one can define like maybe some other entities, but on a very high level. Uh, so essentially, like one can define some mathematical quantity which you can call trust of a user as towards some topic, and then uh, yeah, higher value of trust demonstrates a greater degree of support towards the given topic. So on a very high level, and so suppose like there are two users I and j, and if they both have similar trust values towards the topic, and then basically they share the same kinds of opinions about that topic. And now what can happen is, suppose these two users have almost similar trust factor across multiple topics, like for a large range of topics these users have similar trust, then we can potentially think that, yeah, as I said, these users may be bot accounts connected to the same puppet master. So then one can have this kind of a judgment function or attitude consistency function. Like these are really like just mathematical functions, like which model what I have just said. And yeah, so there's not a lot of like interesting things going on here. And yeah, so but like one defines the attitude consistency between two users I and j using these trust values, and then higher the value of this attitude consistency, greater is the like probability, or there is the chance that the users may be soft puppet accounts with connected to the same puppet master. Right? So just in continuation to this, so what these guys like do is, so after identifying these kinds of attitude consistency functions, they try to model maybe some similar view networks to see whether two users have similar views or not. And yeah, and then they also construct this sock puppet network, which is constructed from these similar view networks by introducing additional constraint. And according to Wu et al., puppet masters have like similar writing styles also. So what they try to identify is authorship identification. So like so apart from like modeling this attitude consistency, so would all say that okay, maybe like this in addition to this attitude consistency, suppose I want to have even more sophisticated mechanism. I want to make my mechanism even more sophisticated in identifying which are software accounts. So what would all additionally say is okay, like puppet masters have similar writing styles, so probably their bot accounts will also have very similar writing style. So one can try to also determine, in addition to maybe opinions, one can also try to determine like writing styles, like, and this is usually done by like so there are some kind of authorship identification techniques where one can learn from certain data, and then like one can predict given some piece of text who is the author of that text. And so like if a lot of these sock puppet accounts uh, will like if we run these kinds of networks on these sock puppet accounts, probably their authorship will be most of their authorship will be attributed to like one unique account, which will be the puppet master account or something like that. So community detection algorithms on sock puppet network can determine which sock puppets belong to a certain sock puppet group, and so on a very high level, this is the idea. So first we saw that so there was this idea by Kumar et al. Where they discussed these kinds of measures like similar IP addresses, temporal proximity, and number of discussions commented upon. And then they also saw about things about ego networks. But then there was an alternate approach by Wu et al. So these approaches might some approaches might give better results in one context, some might give better results in another context. So in Wu et al.'s algorithm, what they essentially, what all the essential idea is, maybe we can leverage machine learning to identify all of these things. So what they say is they try to model like attitude consistency, whether two accounts have similar opinions across various topics, and then they also try to model these similar view networks where they say that okay, maybe accounts with similar writing styles also belong to the same puppet master or something. So yeah. Okay, so ending this discussion on sock puppets. Yeah. Uh, Another thing can be like okay. So these sock puppet accounts maybe okay. Like the one last thing. So maybe these sock puppet accounts are like used by people as a shortcut to become popular on social media, and where what one can actually do is one puppet master can give some kind of premium services where provide one can the puppet master provides services upon receiving payment from the customer. So customer pays the puppet master, okay, like you try to make me famous or make positive comments about me, and then you'll get some payment from me. But essentially there's another thing where there are unpaid services where uh, the users are asked to maybe provide their login details like Twitter or anything else, and then like the puppet master will post positive comments about the user on the network. But note that even though one thing to always note is like nothing is free. So here, like when you are saying freemium services, you are not paying any money, but this freedom maybe usually comes at a cost of like providing your login details to the puppet master, and then puppet master can use your account in maybe some black market activities and so on. So yeah. Yeah, so this is the like these are like usually to get popular on social media. A lot of people, like not a lot of people, I don't know, but yeah, there are like there you will find many people who use these kinds of services to become famous on social media. So okay then maybe uh, once some more discussion on like these social networks. So note that uh, one thing can be actually like so what we just discussed now was sock puppeting, where there is one puppet master who owns multiple accounts and posts using these accounts. But there can be another kind of phenomena present in the network, which is collusion. And what is collusion? So maybe in collusion, suppose there are thousands of users who have like genuine accounts. It's not like these thousand accounts belong to maybe one puppet master, but instead, let's say there are thousand accounts which have like thousand genuine users associated to them. But suppose these users together decide, okay, maybe all of us together will uh, spread hate on the internet, let's say about some topic, or they decide, okay, like maybe some like film star or some celebrity hires like thousand people to say, okay, use your Twitter accounts or something to make me famous, and I'll pay you. So what these thousand people can do is all these thousand people, although they are different entities, will post positive comments about that celebrity or someone. So uh, so this is what is called collusion. And note that this collusion is somewhat different, and we use somewhat different from like sock puppeting, and it has like different techniques than sock puppeting, because some observations which we made about like sock puppeting, like okay, like maybe for different accounts owned by the same puppet master, the writing styles will be similar. But now the writing style will not really be similar for collusive users, because now there are thousand genuine users, so there will be thousand genuine writing styles. And uh, these users will also not really have a lot of similar view networks. So suppose some specific celebrity has paid these thousand users to promote that celebrity. So these, although these users will have like similar views on the topics related to that, will have all of these will have like similar views on the topics related to that celebrity. But on the topics which are not related to that celebrity, these users may have differing opinions. So then, yeah, identifying collusive users is a bit tricky in social networks. So yeah, and like these collusive users are also like you may have heard of like these paid services or services where they provide you with where like they provide you with a lot of Instagram followers or someone at some minimal cost or something. So these services are usually done by these collusive users rather than these bot accounts. And so note that these collusive users are asynchronous, that they do all of these don't act at the same time. Like since these are 1,000 people, these 1,000 people will be doing things differently, like from different IP addresses at different points of time and so on. Whereas in whereas for like fake users, whereas for these fake users or these sock puppet users, it's usually that these have a lot of spike, like all of these posts at the same time or maybe in the same time interval and so on. Whereas uh, these collusive users are asynchronous, that is like they don't necessarily post at the same time. Yeah. So fake users cause these kinds of few noticeable spikes, whereas collusive and genuine users show multiple small spikes in the uh, fraction of users like online at the moment or posting about some topic at the moment. And then yeah, like one can like these fake users can have like some kind of fake following through celebrities, and yeah, and these collusive these collusive users can also like follow some people, and like the activity of like this following, like if these are fake followers, then probably like they fall whenever they start to follow someone, that activity will be like shown a spike. Like a lot of users will be active at almost at the same time and follow like some user. Whereas these collusive users, their activity of like following some users will change uh, over time. Like it won't show spikes over time, something like that. So then how do we detect collusion? Like it seems naturally a bit harder problem than detecting uh, like bot accounts or like fake accounts, because uh, it's like really difficult to identify like whether these are colluding on this specific topic or something else or something. So Chetan et al. Actually tried to solve this problem of detecting collusion in online social networks using an algorithm what they called core rank or core rank, whatever you want to call it. And yeah, on a very high level, although we won't be going into mathematics of it, but you can like anyways read the paper if you want to go into the math. But on a okay, yeah, yeah. But on a very high level, uh, what they define is these um, degrees of supports of a user to, let's say, a certain tweet. Suppose we are detecting collusion in, let's say, Twitter or something. So what they define is they say a user is said to support a tweet T if you maybe retweets or quotes that tweet, and then the degree of support shown by that user towards that specific tweet will be maybe uh, using some weight. So we assign maybe some weight WQ if user quoted that tweet, and WR if user retweeted that tweet. So maybe like the degree of support is like different, like the weights assigned are different for like quoting a tweet and retweeting a tweet. And like, and note that usually WR is less than equal to WQ because quoting a tweet has a higher chance of being a genuine action than retweeting. So yeah, and then they build some kind of a support network. At least like we are discussing how to model this problem of detecting collusion, but we won't go into like the details of their algorithm. So they form a bipartite network where one set is the set of users and the other set is the set of tweets supported by the users, and then they have these weighted edges uh, where the weights are denoted by the supports, the degree of supports from every user to every tweet. And then they try to detect collusion using their co-rank algorithm. Yeah. So you can look at this paper if you are interested in finding out mathematics behind this algorithm or something. But yeah. So yeah. So we just discussed so now we have discussed about like these fake users or what are called soft puppeting, and also about collusions in these online social networks. Now maybe we can come to the second use case, like apart from these. Okay, so essentially we discussed about malicious activities in online social networks. Now we'll maybe come to some other case study or like some other use case where maybe we'll try. we'll try to model the spread of COVID-19 pandemic using the concepts which we have learned in the social network. So we learned a lot of these concepts, these SIR models and everything in the last week itself. I think in the last week I also mentioned that this SIR model can be used to model the spread of COVID-19, and alas, like we are indeed discussing that spread of COVID-19 using SIR model right now. So note that what is a susceptible infectious recovered model, like uh, so people are susceptible to disease. People, so just revising, like susceptible people are people who can become infected. Infected are people are like who have become infected and are capable of infecting others. Recovered people are people who have recovered or become immune to the infection. So if you have become immune, then you are no longer susceptible. So this is what happened in COVID. Like at least like in viruses, in general, in viruses, what happens is you're susceptible. You get that virus, and after you recover from that virus, you develop natural immunity. So you don't have to so it's a high chance that you won't get affected by the same strain of the virus again. And then there are these parameters beta and gamma, where beta is called the birth rate, gamma is called the death rate. These births and deaths are with respect to like the infection. So the rate at which susceptible people become infectious is given by minus beta times number of susceptible people and times number of infected people. Then the rate of and this is in negation because like susceptible people, the number of susceptible people will decrease. And then in infectious people, so number of infectious people are increased using this factor of beta, but are decreased using this factor of gamma, and the associated multipliers are here like beta times Si increase and gamma times I decrease. And then what's the rate of change of recovered people? It's just like infectious people become recovered, so it's gamma times I. So this is an SIR model, and it can be used to model the spread of COVID-19. But then there are like further models maybe which can explain COVID-19 better or something. So there are these SIS model. So yeah, so SIS model is the model where one is susceptible, one can become infected, and can again become susceptible. So this is not usually true for viruses because once you develop immunity to that to the strain of the virus, like it's usually not the case that you get that virus again. But this is common for common colds actually, like because like in common colds or anything like the strain of the virus which is affecting you or causing that cold is actually not fixed. So even though common colds are usually caused by viruses, you can develop these common colds again and again over time because the underlying strains of the virus is affecting you are different. So normally like this SIS model is used to model common colds. So it's apt for modeling infectious diseases that can recur rapidly. So a recovered individual becomes susceptible again. So there is a birth rate beta, which controls like the number of people becoming from coming from susceptible to infected, and then there is a death rate alpha. Uh, so here death rate was denoted by gamma, but here it's denoted by alpha, which controls the probability with which infectious node becomes susceptible again. So yeah, so one can again model like these differential equations and see and like try to solve these equations and plot like how this like S and I thing changes over time. So yeah. And like coming to maybe some more sophisticated models. So this is maybe one of the more sophisticated models because you introduce more states to model the spread of COVID-19. Like this was specific. This is more specific to like COVID-19, like this kind of a model, whereas these models are like more general and can apply to like and can give like good predictions for like in a general context. But if you specifically want to model COVID-19, maybe this say Siddhartha model SIDARTHE, I just call it that is actually more useful because like COVID-19, we know what COVID-19 did and like what are the different kinds of states which can be present in the COVID-19 model. So it's a more sophisticated model. So here like again S is susceptible. So now the susceptible people can contact COVID-19 from 4 different kinds of sources. So we're not just saying that they can come in contact from like infected people, but they can come in contact from infected people, this I, the diagnosed people, D, the ailing people, gamma, and the recognized people. And usually alpha is greater than gamma is greater than beta, comma, delta. And so essentially like susceptible people can catch the virus with the highest probability from infected people, and like then the second highest probability is ailing people. So infected people are people who have come in contact with COVID-19, so they have developed the infection. Ailing people are like who are greatly suffering from the infection. So usually these people, yeah. So these people maybe so infected people are the people maybe who like from which you can contact with the highest probability. Then comes ailing people, and then beta, which is diagnosed people who have just been diagnosed with COVID-19, and comma delta, where delta is like the people who have recognized that they have COVID-19, although they are not diagnosed, but they have still recognized maybe they are showing some symptoms, and then they try to like self-isolate or something. So these are so infected, diagnosed, ailing, and recognized. And then there are these three things also, THE. So these factors are usually for these things are like T is threatened, H is healed, and E is extinct. So extinct is like modeling like death of people, like because like total like in previous models we assume that the population remains constant, but actually like people are indeed dying from COVID-19. So yeah, we have extinct people, and then there are threatened people who are like very critical, and from that they can heal or like they can go to extinct or something. So yeah, so this is the COVID-19 model which was proposed by Giordano et al. In 2020. And there are two more parameters like associated with detection of asymptomatic infected individual. So one very big issue during COVID-19 was indeed like there were like asymptomatic spreaders also. Like there were people who had COVID-19, but they were asymptomatic. And then there were like symptomatic individuals. So yeah, and dependent on testing strategies adopted and so on. So now like again like in this model, uh, what happened was like in this specific Siddharth model, so the what are some specifications for this model? Like asymptomatic individuals can transit to the symptomatic stage where they have been tested positive, or when and even when they are not even tested positive. So if asymptomatic individuals can actually develop symptoms later on, so they can become symptomatic at a later stage. And individuals grow life-threatening symptoms irrespective of detection of their infection. So they can transition from ailing threatened state, and they can also transition from recognized to threatened state. And then there is this mortality rate after showing life-threatening systems, which this rate is like the rate at which people are going from threatened to extinct. And then rate at which individuals recover from all the infected states are like people can recover from an infected state, ailing state, threatened state, recognized state, diagnosed state. So from every state people can recover, but like not from this extinct state, obviously. So yeah. So then if you have all of these as like uh, the characteristics of the model, then one can model the rate of change of population at different stages using all of these sets of differential equations. And like obviously it's very difficult to solve such a large set of equations, but one can still use like computations to at least plot these kinds of like how will the rate of change of population look like for these, or at least what is the population values, at least one can simulate it on a computer or something. So yeah, and then there are like other models for COVID-19 pandemic also. Like when COVID-19 pandemic started, I think a lot of people worked on like modeling how will this pandemic spread out. And yeah, so Gatto et al. In 2020 devised a modification of the SEIR epidemic model, which we discussed I think in the last lecture, where they said that they tried to incorporate spatial characteristics, and they termed this model as CPR, where they try like because like different states have different laws and everything, so they have like the spatial characteristics attached. So the compartment in their model was susceptible, exposed, pre-symptomatic, uh, and then asymptomatic slash mildly symptomatic, hospitalized, quarantined, recovered, and dead. Similarly, like New et al. In 2020 devised a model they designated as Seiru model, which took into consideration the latency period of COVID-19 before which an infected person is capable of transmitting the infection. So a lot of sophisticated models and a lot of research has went into this topic. Yeah. So Weeds et al. Introduced the concept of shield immunity on top of SIR epidemic model to model all of this. So yeah. So I think we have all discussed and we have a good idea of like how to model like these kinds of spread of diseases. So this is also a very important real life application of all of the things which we have discussed over this course. That one can model all of these things as networks and then see like how does this network change with different parameters. Okay then, so maybe so yeah, the one last thing which was discussed in these lectures was some discussion about recommender systems. So if you're not familiar with recommender systems, like on a very high level, I'll just tell you that this is a very huge topic and a lot of research is going into it because a lot of very large companies are pouring millions and millions of dollars into research on recommender systems. So because like all these companies like Amazon, Netflix, the companies which want to sell some products, so they want that the recommendations which their portal shows should be like good for some user. Like if you show the correct, so the idea behind this is like if you show an appropriate recommendation to the user at certain point of time, then it's likelier that the user will indeed buy that product or something. So yeah, so these recommendation users like try to model like interests of some specific interests of like each of the users and like try to predict like what will the user like to see or like to get at this point of time or something. So yeah. So yeah. So recommended systems on a very high level are a subclass of information filtering systems which seek to predict the rating of preference a user would give to an item. And this is used in a variety of areas and like believe me, millions and millions of dollars are going into research on these recommender systems. So Karpagam is typing something in the chat, I believe. I think I uploaded the PDF for the. So Karpagam, you're saying that the PDF for session 8 is yet to be uploaded. So I believe it has already been uploaded. Like, is it not been uploaded? I'll just check. I'll just take a quick check right now because I think I uploaded it. There may have been an issue of or something. I'll just see again. Mm, okay, I'm actually not able to open this. What even is this? Just a second. Okay, so Kapagam, you're saying that it has not been uploaded. Just let me uh I'll upload it right now if that's the case because I thought that I have uploaded. Uh, this is recording. Oh, so sorry. I just saw that it has not been uploaded. I don't know what's the reason. I uploaded it. Probably there was some network issue. I'll just upload it right now, Karpagam, because I think like it's important to. Oh, okay, like I'll just upload it like just at the end of this session. So sorry, Karpagam. As soon as the session ends, I'll upload it straight away. Right now, like there's some issue and like I'm not able to upload it, but I'll upload it as soon as the session is over. Yeah, probably I think it may have been an issue. Like I may have forgot that. I think I uploaded the recording, but not the yeah, but not the session. Yeah, thanks a lot, Kripakam, for informing me about it. Okay, so now, so I think for now maybe we can just continue with the discussion which we were going with. So like we are now discussing about these recommender systems. So should I continue the discussion for now, Kripakam? Like I'll upload the recording later, but for now, like let's just maybe continue the discussion which we are having. So, like yeah, as I was saying that huge amounts of research are going into like recommended system which seek to predict the preference you would give to an item. So, for example, like yeah, personally, like what I usually joke around with my friends is these recommended systems throw your private privacy out of the window because like probably you'd have seen also like sometimes maybe you're discussing some topic with your friend or you're just browsing out it on something and suddenly in your YouTube also or YouTube recommendations also it pops up the same kind of topic which you're browsing upon on some different like browser or something. So yeah, these recommended systems really try to throw your privacy out of the window, but yeah, all the companies try to do this uh, so as to give better recommendations to you and hence like sell their products. So yeah, for example, like suppose there are two users who are similar according to like some metrics used by the like used in the network. So then it's possible like so similar users will have similar kinds of preferences. This is the higher level idea of recommender systems. So if there are two users who are similar and one user has watched something but the other user has not watched, then the other thing will be recommended to the user. So this is the high level idea on recommender system. But note that a lot of sophisticated techniques have gone into this recommender systems. So yeah. So then there are multiple kinds of recommender systems, although we won't be going to the anyone's math, but we are just discussing very high level ideas. You can, if you want to go into the math, you can read about them online maybe. Yeah. But on a very high level, there are like three types or multiple, at least four types of recommender system. One is content based, where uh, one maybe you can buy one something, and then it shows similar content. Like suppose you buy something, and then the recommender system shows you the items which are similar to the item which you bought. So suppose you have bought bread and milk, then it will automatically recommend you like a similar item is eggs. because these are also used in breakfast. So it will recommend that maybe, oh, you have bought bread and milk, so maybe you should buy eggs also. So it shows you what more of what you like. And then another kind of recommender system is collaborative filtering, where suppose there are two users who are like maybe friends or something, and the recommender system knows this, and one user has brought like bread, milk, and eggs, and the other user already bought bread and milk. Then the recommender system will say, okay, maybe you should also buy eggs. Like the kind of thing here. Like if one friend was likes the movie or watches the movie, it will be recommended to the other friend too. So essentially, collaborative filtering shows you more of you what your peers like. Like, so one thing is content based where it shows you what you like. Collaborative filtering is where it shows you what more of what your peers like. And the third thing is knowledge based recommender systems where you can specify maybe your demand. Like, okay, I want some so suppose you're searching on, let's say, on Amazon about you want to buy some laptops. So you just don't go and straight away type out the model, let's say. You just type out maybe, okay, let me search for laptops under like 1 lakh or yeah, something. And then it shows you a list and yeah, the kind of laptops which you will possibly like. So so you just say like maybe I want to make breakfast, and then the recommender system will recommend you what kind of items will be suited to best to your needs if you want to make breakfast. So it shows you according to your needs. One thing is according to what you like. Another thing is according to what your peers like. Another thing is suppose no one knows what, if you're not like sure of what you like, but you still have some kind of needs, and then the recommender system can recommend you some things. And then like although these are the high level three kinds of recommender systems, you can take some kinds of hybrids where you can take combinations of various inputs or mechanisms. So yeah. And why recommender systems? Although they come at cost of a lot of privacy of the users, but they are like helpful for the user's perspective also because it helps them find relevant items, it helps them browse efficiently or effectively, and enables users to each other in collaborative filter. And what's the use for providers? Like it sells more items, it sells rare items, and increases user satisfaction. So yeah, so this is better for provider, and this is also better for user. So one way like so there are different kinds of recommender systems, and like a lot of research goes into this, and one kind of recommender systems are like which are like quite popular are graph recommender systems, where essentially the underlying idea is like a lot of networks are like anything can be modeled as graphs, like social networks, gene interactions, molecules, and everything. So graphs have the capability to learn really complex data, so one can try to make recommender systems after out of graphs also. So, for example, suppose you can have a graph G where the nodes are the items, for example, users and the products, and E is the relations between the items. Example like, so an edge is there between a user and the item if that user purchased that item or something. And then there is the aim is maybe graph, uh, to learn a graph learning recommender system model that generates optimal recommendation results with optimal model parameters that are learned from the content information of the graph. And then this can be modeled mathematically also, but yeah, on a very high level, like since we have not described what are these parameters and what are the loss functions with respect to which we are want to optimize, the high level idea is you want to learn a model that generates optimal recommendation results for you with respect to like what is optimal. It is with respect to some kind of a function which will depend on your needs and everything. But yeah, so like you can read about these maybe yeah, a lot of this, not a lot of this was discussed in detail in the lectures, but still you can watch the lectures if you are interested in these. But I'll just give some high level ideas of the components involved in these kinds of graph recommender systems. So there are these concepts of encoders and these variational autoencoders. So these are like very useful in general in machine learning domain, these autoencoders and everything. Uh, and yeah, these graph recommender systems heavily use these kinds of things. So so essentially what autoencoders do is they generate images similar to original input. So suppose you want, so these autoencoders are essentially like some kind of machine learned models where what they do is they can encode some image, or like they try to compress some image in some other code, and then they can also decode the image. So these autoencoders generate images that are similar to the original inputs, whereas you can make some variation to these and call these variational autoencoders, which can generate new data from the original source data set. And these variational autoencoders are like useful components in these graph recommender systems. So I'll not say a lot about these, but just like I think since these definitions were discussed in the lectures, I thought like it was important to include these. Although like I don't think they are given any kind of mathematical treatment in the lectures. If you want to learn more about them, you are free to learn it on various sources. But yeah, for now, like I just want to discuss these definitions of what are these autoencoders and what are these variational autoencoders, and they are useful for these graph recommender system. In general, they are useful in a lot of machine learning, like not just graph recommender system, but in NLP and all. But yeah, in the context of graph recommender systems, also these are very useful. So okay then. Uh, Uh, I guess this was it for the like summary of this week's lectures what I had for the day. And now we have like a bunch of questions, just 6 questions today, which we'll discussing. And I think since like a lot of the things we discussed today were quite simple, nothing was too complex. So the questions are also quite simple. I think in this week's quiz also like you won't be having much trouble, but still we should discuss these. Uh, so first question is maybe which of the following is not a feature of a typical sock puppet? So Karpagam, okay, maybe Karpagam arrived a bit late, or so would you like to answer this question, Karpagam? Which of the following is not a feature of a typical sock puppet? Accounts that post from any same IP address, accounts that post only positive reviews, accounts that post at similar time durations, accounts that make similar edits. Okay, so Karpagam is saying option B. So yeah, so Karpagam is saying that accounts that post only positive reviews. So good job, Karpagam. Yeah, this is definitely not a feature of typical sock puppet. Sock puppets can post like negative reviews also or something. Essentially, the idea is that all of them will share similar reviews, but it need not necessarily be positive. So yeah, so this is option B. So I'll just underline this. Discussed in the lectures. So yeah. So let's do the second question. So sock puppets tend to be more synchronous in their actions than ordinary nodes. True or false? So again, Karpagam, I think you can try to answer this. Are sock puppets more synchronous in their actions than ordinary nodes? So synchronous is essentially so what synchronous means is like performing the actions at the same time. Asynchronous means performing the action at different times, and synchronous means performing the action at similar times. So is it true or false, Karpagam? So yeah, so I mean true. So yeah, good job, Karpagam. Like software tend to be more synchronous in their action. So yeah, this statement is indeed true because like all of these are bot accounts operated by the same puppet master. So all of these will likely post at the same time. So this was also discussed. So good job, Karpagam. It was true. True, as discussed in the lectures. Then coming to the third question. Okay. So you are run out of network, so not able to send it quickly. Oh, okay, Karpagam. I think then we'll try to finish the wrap of the session as soon as possible. Also, if you are running out of network. So what are so I'll maybe then I'll just discuss these questions. So what are premium collusive services? So this was also discussed in the lectures that The premium collusive services actually require some kind of payment to make you famous or something. So it's like premium collusive services is giving money so that you can reshare some content. No, like it's like receiving upwards to each shares in return for money. So this is what a premium collusive service is. Again, this has been discussed in the lectures. So yeah. So then coming to question 4, like collusive users tend to have less topical diversity and have longer support time than regular users. So which of these things are true and false? So note that so we already discussed that collusive users. So if the users are like colluding on something, then it's possible that yeah, like they'll want to make some person famous or something. So what they'll have is like they'll have more topical diversity. So and what is topical diversity? So like topical diversity is discussions on various topics. So suppose some users are collusive, uh, then or like they are providing services to be collusive, then what can happen is if one person is paying payment for them to make that person famous, another person is saying paying payment to them to make some other topic famous or something. So these collusive users will be colluding on various topics, like on once maybe one celebrity, some other topic, and so on. So they'll be like colluding on various topics, and so they'll be posting about multiple topics. So they have more topical diversity. That's why. So this is option A is false. So so like so one is false. Maybe I'll just write the explanation later, or like just write it right now. Since collusive users can collude on multiple topics, hence they have more topical diversity. And they have longer inter-support time than regular users. It's also false because what is inter-support time? It's like if one person posts about something, some other person supports your views or supports your tweet, and for example your tweet, or like upvotes your tweet or something. So note that in collusive users, like if a lot of users are posting, then it's likely that uh, if I post and I have some colluding users with me, then the other users will upvote my tweet faster. So that's why they have smaller uh, inter support time. Also, collusive users have smaller inter support time. So both of these things are false. So option C is correct. So hence option C is correct. Doesn't lie. Okay. So then the fifth question is in the SIR model. This is model. An infected user may directly move to the susceptible state. Is this true or false? So note that in SIR model we just discussed that a susceptible user moves to infected state, and then an infected user moves to a recovered state and does not like, and then the recovered person cannot get susceptible again. So a infected user does not move to a susceptible state at all in the SIR model. So this is actually false. So this is discussed. Yeah. So coming to the last question of the day. And last question of the problem solving session for this semester. In which of the following information disorder there is no intention to cause harm but has the potential to fool? So this is what we just discussed in the beginning. So there is no intention to harm but potential to fool someone. So this is satire usually. So people joke around the internet, and yeah, it can be taken as serious by someone, although the intention might not be to harm someone. So option D, and this is also discussed in the lecture. Yeah. So we discussed this actually at the start of the session. Yeah. What is satire/parody? So no intention to harm, but has potential to fool. So yeah. So okay then. So I guess so yeah. So Karpagama, I guess this was it what I had for the day. So we discussed 6 questions and summary of this week's lectures. And yeah, so this was it, the final session for this course, at least the problem solving session. Just as a reminder, we'll be having a like summary session where I'll be like trying to uh, very briefly go over topics discussed over these 12 weeks. Uh, so yeah, and yeah, I guess this wraps up our problem solving sessions component of the course. So thanks a lot to everyone who's watching on YouTube, and thanks Karpagam for joining the session. So I guess if there are no doubts, we can close the session now. Okay, Karpagam. Hopefully I'll see you tomorrow, and hopefully I'll see some other people also in person in tomorrow's session. Okay. So till then, goodbye, and like all the best for your exams. And yeah. Okay then. Bye bye.